I'd like to be the first to welcome you to our webinar, Raising the Bar, Milling Strategies and Tools for Implant Bar Production. We're basically going to take you on a tour and a deep dive of some of the challenges that the industry faces when producing these types of dental prosthesis. We've been approached by many customers with problems relating to the implant interface geometry not being accurate, not getting a passive fit. Maybe just the way that the strategy is in the CAM software isn't quite what they're looking for on the final result. But all this to say, these are big challenges, but as a technology integrator in the dental industry, these are the challenges that we face day to day. But don't take my word for it. We always like to bring in the experts from the industry to weigh in and kind of tell you how it is from their perspective. I do lead the dental team at Proto 3000. My name is Scott Corman. On the call, I also have other members of the dental team, Mr. Kaveh Shams. If you want to wave and say hello, Kaveh, you can do so. Everyone's muted, by the way. There's Kaveh.
Hello, everyone.
Great, great. We've also got Mr. Ivan Barron on the call, and he'll be able to talk to you a little bit about the consumables that you go through in milling challenges, tools and consumables and so forth. We've also got Mr. Mike Wang and Mr. James Bliss. So we're in full force from the Proto 3000 team today. Mostly we have them for support with the Q&A that will happen towards the end of the webinar. The format today will be a brief intro, which we are in the middle of. We'll jump into the content next. We'll actually show you CAM software and go into detail, and then we'll have a Q&A session at the end, which usually proves to be quite valuable. So I'd like to introduce now our special guest today. We have Mr. Jordan Greenberg with Follow Me Technology Hyperdent, as well as Mark Fisher, the wizard. I don't know, can I call Mark Fisher a wizard at this point?
Oh, he is a wizard.
He's reached wizard status? Okay.
Yeah.
I thought so. Usually we send in Mark when the gloves come off. So we're happy to have Mark on the call here as well today.
Yeah, and I'm happy to have him doing the driving of the Hyperdent software for me because he's much more competent with that than I am. So just to give you a very brief history of my background, I actually worked for a machine manufacturer that specialized in these implant-based type restorations. That's when I started to use and become familiar with the Hyperdent software. Loved it so much and created a relationship in which I was afforded the opportunity to start the North American branch office. We brought Mark in because he was an all-star at all of the production facilities that he worked at that utilized Hyperdent, which ranged from high production crown and bridge facilities to facilities that specialize specifically in implant restorations like some of the ones that you'll see today. So that's who we are. Did we want to wait another minute, Scott, to make sure that everyone had a chance to join, or?
Well, I like to run my webinars on schedule, so I guess we could wait a couple minutes. I'll kind of leave it up to you. If you wanted to talk maybe a bit more about an introduction to Hyperdent, you could do so, or jump into the content. It's really up to you.
We'll jump into the content. What we'll do is we're gonna pull up a case that may seem familiar to, if you're already using some sort of CAD/CAM solution, milling solution in your facility. I know we have a wide array of attendees, but if you're already doing some milling and some machining in your own facility, you might already be able to do some of these hybrid type restorations that utilize tie bases cemented into the part itself. This is not what we're going to talk about today. These parts afford you the opportunity to use equipment that isn't as robust. It affords you the opportunity to use equipment that isn't as accurate. And that's because typically, just like any crown and bridge, when you're cementing a tie base, you're doing it with some sort of slop, which can be corrected by when you're seating these parts or finalizing the parts and the components. So the main difference that you'll see in our program that differentiates this type of part from the type of part that will be milled directly from metal and will be inserted directly into your either implant restoration or multi-unit implant restoration, is what we call the implant module, and it allows for the export, for the import of a third party or from a secondary interface geometry. So Mark, if we could jump right back to that first one real quick, the hybrid type part.
Yep.
Then the difference here, or what you'll see between the two, is that we utilize the STL information, the design information, and we machine specifically or directly off of these surfaces. So it's not as important. If we zoom into the implant interface, you'll see some faceting on that implant interface. And I know the light has to hit it just right. There it is. And those inconsistencies or lack of precision is something that when you're cementing a tie base into this type of restoration, it's okay to replicate that slight imperfection. It's not going to affect the fit of the actual interface geometry, because that's not what interfaces with the actual implant or the multi-unit abutment. Now, when we switch over and we're milling the actual titanium part that will be inserted into the mouth, or at least interface with the implant itself, there's an additional level of accuracy that needs to be practiced. So we can make the bar transparent, Mark, and it'll make it so that we can understand a little bit more about what's going on here. So what Mark has just made transparent is the STL bar shape that was exported from the CAD software. What we've done, and we're going to go into a lot more detail regarding these sort of features, is that we've imported our own implant geometry. And this information that you see in blue and one in yellow, which is currently highlighted, those are important for multiple reasons. And what's happening here is that the imported information supersedes any sort of STL specific information that you're getting. Now, you're going to see a few things that are different. If we zoom in right by the screw channel, you're going to see that these screw channel diameters are dramatically different from each other. If you see the very top section of the screw seat area, that's going to extend in terms of diameter all the way to the top of that channel. Now, that is the proper screw dimension, and the output STL file is something that is too large. So all of that information inside that screw seat area, all the way through the screw shaft, that's going to be the correct diameter because we've imported a more accurate shape. So there's three reasons, or there's three things happening when we import these external geometries. One is we're guaranteeing that this is the correct shape. Two, we're guaranteeing that this implant geometry is in the exact right position. That's height-wise on the z-axis, or if you slid, let's say we slid this up or down, and you can see that it's kind of meshing perfectly with the STL file on the edge or the seat surface. And then lastly, we're also creating the milling instructions in order to go and replicate this geometry over and over again. So not only within this one part, but within all your parts. A challenge that maybe not an individual lab or a doctor's office, they wouldn't really see this type of challenge, but a milling center often sees challenges where they're receiving files from a lot of different customers with a lot of different CAD systems, with a lot of different scan adapters. So when you have a wide array of customers like this, you're going to see a lot of different inconsistencies with the files that you receive. What Mark has just pulled up is a perfect example of one of the worst case scenarios where the STL file is exported without any sort of information as to what the interface geometry should be or should look like. So by importing these external geometries, that will supersede these quote unquote blanks that you're seeing in front of you. And what we're able to do is successfully mill this geometry despite the fact that there's almost no information provided for us in terms of how to mill this geometry shape. So very cool. Mark, is it possible? Let's get a little deeper into the details as to what one of these implant geometries looks like when it stands alone. This is what you're seeing right now, is the type of stuff that is more accessible or usable for the end user. What's really happening when we pull back the covers and take a closer look is that we could individually define features, planes, attributes on every single implant type that we import. So what you're seeing right now is basically an area, and this is a very simple geometry in which we define specifically what the milling parameters are in order to produce that exact geometry. And that's what we're replicating over and over and over again in all of our bars, all of the implant locations, to create that consistent fit and finish that you're looking for. So
you can
Mark,
also see that
if you want to take the reins and show maybe what this sort of category, which I guess is visible in the bottom left corner, correlates to in the actual template parameters, then why don't you show us a little bit about what's happening? Again, this is the type of information that is not necessary for the end user to know, but this is when you call Proto and you say, hey, I'm having an issue with this bar, or I have a new geometry I want to machine. These are the tools that they're using in order to go ahead and fine tune an application for exactly your needs.
Yeah, sure thing. So the nice thing about this geometry is that you can tell based on the other ones that we looked at earlier that there's no heavy faceting on this STL at all. It's a very fine resolution. So your file from whether it be extrapad or 3Shape or wherever, the resolution could be poor or wrong, and this is going to be superimposed on your bar, and it's going to be milled instead of anything that comes directly out of your CAD software. So we're basically marking features on here. Something like the multi-unit is going to have 1 or 2 categories, some more complex geometries. They're going to have even more categories that maybe a Straumann Sonocta that has a slight internal cave on it that you need to bring in a smaller tool. So it just varies based on each geometry. But what's going on in the background, if we go to our milling strategies, nice little list here, is we have different categories, and we're defining, and again, this is all done on our level or on Proto's level, but just so you have a tiny peek at what's going on. Basically saying that this style implant, this sloping chamfer, this tight corner, whatever the case may be, is going to be milled like this. It could be an external feature on an outer wall. It could be something on an inner wall. The usual feeds and speeds and stuff like that you've probably heard discussed in milling. But this is all called up to mill this at a very precise step down in resolution. So this is kind of a peek at what's going on in the bar strategy. So I'll probably load one in here, and for those of you who aren't familiar with some of the usual workflow in Hyperdent can kind of pay attention a little bit closer than those who are using it already. But you're just going to make sure that your bar looks good. If we've got geometries on here, and
I'm just going to interject real quick. Mark pulled in a bar, and as you can see, most of the part features were already identified, whether it be the screw channel, the abutment base, or the geometry which was imported. As long as you're using or saving the exported information from your CAD system, then all of these attributes and features are already going to be defined when you pull it into Hyperdent. It's not something that you're going to have to manually define yourself, and it's not something that you're going to have to introduce some form of user error when you're loading these parts. Maybe I loaded the wrong implant geometry or implant type. As long as you've chosen the right implant type in your CAD system, then when you continue to go through the rest of your steps, once you get to the import into Hyperdent, then it will already be completed. Basically just as easy as nesting any sort of a crown, a single crown, because everything's already defined.
Sure, yeah, I'll give them, so when you have your part on here, a lot of you, you can load any geometry on your site that you want. Down here at the bottom, you have your prepare wheel. You're going to go to implant interface. And then down here at the very bottom, you're going to have your type of geometry. Whether if you want to bring it in from an external source, you're going to hit external. And then you basically have a folder that it goes and looks at, and you have different brands and sizes, and this is how you choose manually which size that you want. There is an extra file. It's probably more on an individual basis will help give you this demo, but basically it's a very small text file that would go within here, and it might say we're detecting what CAD library. So this is over here on the left side. This is what you're calling it out of 3Shape or ExoCAD. And you can basically take that information and say, yes, it's called this, but when it gets to Hyperdent, I want to call it this. And then these geometries are going to be automatically imported on your part. And you can even account for if there's any sort of Z or platform, if it comes in and maybe the scan adapters that you're using, it shifts it by 0.5 millimeter or so, we can automatically accommodate for that shift as well. It's a really small text file. I'll just show you real quick just so you see how small it is. Basically have this library here equals this library in Hyperdent. So it's very, very small. And then you can move it up in the Z-axis, or you can even rotate it. So that'll be hopefully as technical as I get on this call.
Mark has a little bit of a problem where he starts to get on something that excites him. It doesn't excite the rest of the world, and he talks about it a lot. So
if it saves people dozen clicks a bar, so it's nothing to skip over.
Sounds like typical wizard behavior to me.
We need to get him a hat for the next webinar that we host.
Ooh,
so even if you have nothing, let's pretend that you have just a bare bones STL.
Perfect.
You can mark an implant, which is basically just giving it the position of your implant, and it's still not like I just threw this screw channel on here manually. It's still not right because it doesn't even include like this screw through hole. But once I import my geometry, it overwrites any of that bad, even manual marking that I just put on there, because it handles this distance here. And again, all this is super critical for you to have a solid screw seat and it not pull through or anything like that, versus something like a zirconia over a tie base where the stop distance on that doesn't matter as much because the tie base is going to handle all that information. So that's everything that's going on with manually importing it. You can even make adjustments here if it doesn't hit that platform correctly.
Perfect. Yep. And just to recap, that's like we said earlier, if you're a milling center or you're receiving files from lots of other doctors, labs, whatever the case may be, it can be a struggle to get the entirety of the information that the CAD system outputs. So it doesn't make it so that the bar is completely something that you cannot mill or cannot approach in that instance. So what you just saw Mark do was import the same geometry that was automatically imported into all those other locations, meaning the quality, the shape, the position of that implant location is going to be exactly the same as all of the other bars that you produced with all that great information that you've received.
And I assume there's some people on this call that are at least to this point already. And let's pretend you have a implant that comes in wrong. It comes in high base. It's based on the 0 point of your CAD system and everything. Down here at the bottom is my favorite tool. You can switch this to automatic mode. And then this is going to be a lot like CAD systems. You're going to hit a dot on the lip of the multi-unit, and then you're going to hit a dot on where you want that to align to. And you can tell if you were watching my screen while Jordan was talking, I shifted it up by 0.5 millimeter, and I just automatically corrected that 0.5 millimeter shift down. So I'm not sitting there just eyeballing where this thing needs to go, because the platform, the lip of the multi-unit was accurate.
Yeah, that's exactly right. And right now we're getting into to details that are usually not part of your day-to-day routine. Again, these are unique cases that were delivered to your lab digitally without the information that you need. It's when you can't communicate what it is that you need, or you just can't get it from whatever system was outputting your customer's CAD info. Typically, when you pull on that bar, it's going to come in as needed. And then Mark is actually taking the reins right now and is going to finish nesting it for us real quick. So. We have some automatic connector operations as well. A lot of times, and Mark, you could probably talk a little bit more about this than I can. It's usually easier to just come in and define them individually in most cases. Yeah.
Yep. I would say, depending on, you know, how many connectors you like to put on there and everything, I usually just put them on manually. Automatic can do a pretty good job, but.
And actually, part of the struggle that you're seeing right here when Mark's trying to define these connectors is that these are very straight walls to our bar, and the software will typically try to put a connector right on the equator of a part. And by equator, I mean when you're looking at from the top and when you're looking at from the bottom, basically where those two visible sections meet is where we try to place a connector. That reduces the amount of undercut area you're going to have underneath your connector, between your connector and your part. Just the physics of the general machining parameters. So.
Yep.
And also you see that Mark is not overcrowding the bar. And this is one thing we always tell the customers, that the way that you connect your supports, the way that you nest your bar is very important, and helps you avoid unnecessary tool breakage and accuracy of the part time to time. So you can see that he's selecting those areas, and we always cover these things in your training. As you can see, we don't put too many supports close to each other, because that will create some sort of tool trap, as we like to call it. And that will increase the chance of tool breakage. Mark,
yeah, that's a good point. And these tool traps, sorry, Kyle, you cut out for 1 second. I didn't mean to interrupt. Yeah, and these tool traps, or just, you know, generally too many connectors, the tool has to pick itself up and move around each connector. So that costs you a little bit more time, you know, when you're doing the finishing tool pass from the top and from the bottom. So.
Yeah, and you have to sometimes there's multiple options. We won't get into all of them today, but there's options too to have more of an actual circle up here, and this actually works better on bars. The other one, if you're doing crowns all day, works extremely well just from the top, but with bars you have a little bit.
And back to, you know, implant specific features, we do have an automatic connector creation tool that actually puts just one connector on each side of each implant site, and that's sometimes a pretty good starting point for securing your bar and not having it crowded too much, which Mark just did.
Yeah,
maybe you would want to add an extra connector to the base of each one to get that cantilever at the end, but other than that, it was as quick as just clicking on the part itself and creating those connectors automatically, and now he's just deleting a few off that were slightly crowded. So.
Yeah. This one here, with all the implants and everything on here, it would be ready to go. You know, a lot of one of the other most common issues I help people out with bars is high angles, you know, something that might exceed the limit of what the machine can do. The IMS I-Core and all 5-axis machines have an axis that can spin 360 degrees. And so if you have a really high implant angle that's creeping up on the most that the machine can do, you can hover over each site and it will tell you your maximum angles. But if you visualize and you make the machine tilt, so it has to use the axis that spins 360 degrees as opposed to the one that tilts up and down and only, you know, can only go so far. You'll have you'll have the most success in getting the calculation through. Hyperdent, of course, runs collision checks, and if you exceed that limit, it'll let you know. But just to have the highest chance of success on the first time through, visualize how the machine moves.
Yeah, and to build on that, just a generality with Hyperdent that I've experienced is the safety and consistency of our collision checks. You might have had an instance in the past with other CAM software where it's not tracking what's already been milled and what material is remaining. And sometimes that has caused you to possibly break a tool because you plunge too deep into a screw channel, and maybe the tool is simply not long enough. Hyperdent has the tools available to do one of two things in situations like those. One, not finish the screw channel and just avoid the shink of the tool, but continue to mill the part and not air out. And then the other option is for it to say, hey, something's wrong. I'm not able to get to the bottom of the screw channel. I'm gonna present you with an error, and you're gonna investigate why there might be an issue. So when it comes to tilting these parts at very high angles, we have the fixtures from the machine, the clamping abilities of the machine and the fixtures surrounding it. So you can proceed with the confidence that your tool, your spindle, your shank, your ring on your tool, it's not going to make contact with anything hard or the material itself. So it's a nice confidence to have. Mark's showing us some toolpaths. He's getting a little wizardy again. So Mark, what are we looking at here?
So yeah, you just see that even if we brought in that file that had the STL completely blocking, you're still going to have the geometry milling through that STL, which is would be pretty much impossible to do with any other workflow where you're just trying to mill off the STL.
Yep. Very cool. And then speaking of toolpaths, you were actually looking at one of the implant geometry parameters earlier. I think that was for category 1. I wanted to maybe take a closer look at the tool, the actual profile of the tool that mills category 1. And I think that Ivan might even show us an example of what this actually looks like in the very near future when he chats about tools for a bit. But what we're looking at here is if we even get close to the tip of that tool, you'll see if you're used to milling any sort of organic shape crown bridge, even the full arch hybrid that we pulled in earlier, you're typically familiar with a tool that has a complete radius. We call it a ball nose. However, when you're milling implant-based restorations, there's a lot of geometric elements to these parts that aren't required or aren't necessary to mill to completion in other types of parts that you're familiar with. So that might be the screw seat area, which is a perfect 90-degree angle and is quite long in many cases. So we need a pretty long tool to not only get the full depth of the implant channel, but a sharp corner in order to make the final cut at the bottom of that. And then obviously on the inside of, let's say, like the multi-unit geometries we're looking at right now, maybe these have been radiused, and that's another thing that you might get from an STL file. But if that's the case, it's not the most effective way to produce that part. So again, we use right hand or 90-degree tools on the cutting edge. And then Mark is also showing us a drill right now. So that's another tool that's not necessary when you're in softer materials. You could pretty much spiral down through a screw channel. In titanium, chrome, cobalt, hard metals, it's usually best to use a drill like you would on like any sort of electric hand tool that you've used before, with very long flutes that evacuate all that titanium out of the hole, and then come back and finish it with an end mill that would widen it to the proper dimension. So just tooling in general is very important to pay attention to when we're milling these different types of applications.
Yeah, Jordan, that's an excellent point. Nothing lives in a sandbox by itself. Everything's interrelated, of course. So using the right tools for the job is essential. We've got Ivan on the call. Ivan, if you're able to turn on your mic and camera and talk a little bit.
Yeah, can you guys hear
about
me?
the tools. Yeah, we can hear you.
Perfect, perfect. So yeah, let me just share my screen here. Okay.
This will be brief. Ivan will just kind of give an overview from a materials and tools perspective, and then we'll hop back into Hyperdent.
All right, so can you guys see my screen? Good to go?
Yep.
Perfect. Yeah. So again, thanks for having me on the call. Good afternoon, and to everybody on the call, and good morning to anybody on the West Coast. Again, my name is Ivan Baird. I'm actually one of the newest recruits here at Proto 3000. Again, my duty here is the materials account manager. So I'll be covering the wider range of tools and materials, covering for any of the dental machines that we actually do carry. So again, I just wanted to just briefly go over some of the materials that we actually carry regarding what these guys at Hyperdent are talking about regarding the Cobra Easy Mill and the titanium grade 4 and 5. So as for the Easy Mill, again, regular chrome cobalt have different casting and cooling methods, which usually produces various amounts of crystallized particles within the actual material itself, again, which causes in-tool breakage. As for the Easy Mill material, it has a precise sintering process, which usually helps reduce the buildup of crystallized particles within the material. Again, it offers that minimal wear and tear of the burrs, higher milling speed, better grindability, and offers a shorter process time in regards to your milling system. As for our titanium, we have grades 4 and 5. Again, this material offers consistent quality techniques, for crowns and bridges, as well as bar restorations and substructures in the anterior and posterior regions of the mouth. The titanium alloy does offer higher strength properties, and capable of baking on ceramics that are compatible as well. And moving on, give me a second here. Yeah, so in regards to the tools, a lot of people they're familiar with the IMUS tools, but here at Proto 3000, we wanted to manufacture a tool that's actually a little more superior, hence the name, the superior tool. And these tools were created for those customers who were looking for an alternative option when it came to burrs. Some of the common issues that clients were encountering that I've noticed were, tool breakage, increased wear and tear on some materials, difficulty getting parts in, the amount of suppliers, as well as lack of support and lack of inventory. And mainly turnaround time. Again, our superior tool offers a little more bang for your buck, if you mind me saying that. At the end of the day, again, these tools offer a little alternative for burrs, an alternative for your, chrome cobalt, titanium, zirconia, PMMA, and glass ceramics. So, and again, I don't want to get too in depth into this, but again, these tools may be a little bit more in cost overall, but offer a 20-30% longer lifespan versus some of the standard burrs that you guys are currently using. So and again, if you have more questions, feel free to contact me directly. My contact is there at the bottom at ivan@proto3000.com. If you have any questions, looking for pricing, etc., I can definitely fill you in on that as well.
Great. Thanks so much, Ivan, for briefly going over that. Really, guys, this is a result of the type of approach we take as a company. We really try to be customer centric. Customers come to us with a tool that they don't have, that we don't have either. Well, we go to the market and we figure it out. Who has the best software, hardware, tools, consumables? We partner, we understand how to integrate. So this is an example of that. If you do have tooling and materials questions, please do reach out to Ivan. Back to the boys at Hyperdent, Jordan and Mark.
Just to wrap up some of the conversation we just had regarding tools, consumables, even costs. I've rarely found that a more expensive tool has actually cost more in terms of the general ROI. I know Mark could probably even discuss this a little more than I can, and same with Kaveh. We've done a lot of testing on this, and I could also confirm that when there were, let's call them holes in the offerings from Proto, from us, from all of our vendors together, Proto has worked with us very closely in order to source what it is that was necessary in order to fill those holes, whether it be something in our parameters for toolpaths, a specific tool geometry, or whatever the case may be. And we've had a lot of success because of that. So moving back to the HyperDent software for just a few more minutes. I know we're approaching our Q&A time very shortly. We do have a few advanced features that we might want to showcase. I guess maybe Mark, if you want to highlight a couple user-defined areas to show the final result, or at least what would be a better result on something
absolutely.
like that retention bar.
While Mark is looking to show you the user-defined area, that is a very, very powerful tool. I was just adding something about the Hyperview, another really amazing tool offered by HyperDent, which is the post-processor of this software. It does a lot of things. One is the simulation. The other thing that I really like about this part of the software is the ability to crop the NC file. We all milled parts in the past, and time to time, for any given reason, you have a tool breakage or your machine stops. There are many reasons that your machine stops in the middle of milling process, and many of the cams out there, they just, you have to start from scratch, basically air mill and waste your time until you get to the point that you broke the tool and carry on milling. With Hyperview, you can crop your NC file with a bit of understanding of where you had that issue. You can come back to the NC file and you can see Mark is showing the different parts of that NC file, different lines of that NC file that includes those G codes. And you can start your milling right before when you broke the tool. I just wanted to add that this is another amazing tool that HyperDent offers. It's very helpful.
Sure, probably Kaveh and I's favorite that I see used is, say for instance, you want to test and you want to see how an implant fits on an analog maybe beforehand. You could delete out the connector cutting at the end, and if something if you wanted to take a second adjustment at it, you haven't weakened those screws 90% to maybe do something later on to it. So it's a nice tool, and looks like that other bar got done. And let's see if I 10 minutes, not too bad for a bar with that many operations. About 3 hours mill time. So I think that's pretty ballpark for the basic designs. It's got 6 connections on it. It's got a little more than an all-on-4.
Yeah, I think a 3-hour milling time significantly beats a 1 hour or a 1 week delivery time when you're outsourcing these types of parts. Yeah.
I think so.
So I think what Mark's pulling in now is a case that might need to utilize or not. It's not necessary, but it would create a better result if you utilized a couple additional tools that we have for making sure that you've milled all of the undercuts on your part, many of which would be milled automatically, identified and milled automatically from our software, and then others which require a little more insight and experience from the end user.
Sure. So we have there's various ways to get undercuts in software. There's automatic toolpaths that can come in here and split this job up and do 3+2 operations all around the whole bar. So you'll see the machine tilting slightly off axis and dividing this up into all these little slices and going back and forth. If you have a C-clamp, you might want to try to utilize more than what a 35 or a 10 or so degree tilt could get. So you might want to hold this bar out here. And then we have this icon called user defined area. You can show your undercuts, which is just simply bird's eye view. When we say undercuts, most people know what that means, but it's just bird's eye view, what you can't see from the square top and square bottom. So it's anything hiding underneath that view. And you have different tools here that you can use. But basically, when you're drawing these on here, you're looking bird's eye view right now for how your milling tool is going to get these undercuts. So, you know, you might decide that that hitting it from this view right here, there's a tool that just sort of selects that area, is going to create a nice tool path, and it's going to save you from hand grinding this area afterwards. And it might get even a little bit more than something that tries to automatically just get 10 degrees worth. I'm tilting, you know, close to 30 degrees down here if I look at my angles. So it's a nice, it's going to make your life easier. And you have different tools around here. If different, depending on the type of, you know, this is going to be a little speck down here, and you could just try to get this whole area together at the same time. So this is just creating tool paths that are extra for you, that it's going to have the mill do this area for you.
And the nice part about this tool from an efficiency standpoint is other CAM software typically approaches this type of problem by refinishing the entire surface of the bar from this new angle. So what Mark meant when he said we're looking at from this bird's eye view is pretend you are the milling tool, and the direction in which you're looking is your approach angle when you machine this bar. Now, because there's a C-clamp or an open clamp fixture, we have complete access to the facial side of this particular bar. So you could tilt it all the way to 90 degrees. Now, what he's doing is defining the boundary in which we're going to apply this additional tool path. So you see, most of the bar is not undercut. Only a small percentage of the facial side of this bar has undercuts. And that's the only area you want to come in and reapproach the machining for that facial side of the bar. If you wanted to just blindly go in from 90 degrees and refinish the entire surface, that could take, I don't know, what, 20, 30 minutes, when this additional tool path might only take 2-3 minutes of additional rest machining. So I think we're looking for one of those tool paths right now.
Yep.
As Jordan and Mark take us through this, I just want to call attention to the Q&A chat at the bottom of the screen. If any questions pop up, even if you think it's a quote silly question, this is how we learn as a group. So ask it. You never know who might benefit from the answer. And it's just at the bottom. Go ahead and type it in there, and we'll get to it shortly.
Very good. Yeah, we're wrapping up basically our planned content, let's call it. So if there are any questions on the chat box that I haven't noticed, or that you guys want to chime in and ask us, then please feel free.
Well, it's 2 o'clock now. Just to sort of build on what you just said there, it's a learning journey, right? When you set out to do some of these applications, you learn about the tools that are available, you become educated, you decide on the right tool for the purpose, and then ensure that it works within your existing workflow, and upgrade or make changes as necessary. And this, of course, depends on your level of commitment to quality yourself, either as a clinician or a dental lab technician. So the good news is Proto 3000 exists for this purpose. We are here to not know everything necessarily, but we're here to plug you into the resources that you require. So I want to thank Jordan and Mark for taking time out of their very busy schedules to join us today. That information was very valuable. So thanks again, gentlemen, as well as the rest of the Proto 3000 dental team, Ivan Barron, Kaveh Shams, Mike Wang, and James Bliss. We'll be doing these webinars as frequently as possible. So stay tuned for the very next one. And don't forget to keep smiling.